Welcome to qnawire.
Have a cogeneration plant modified with regeneration. So cogeneration and regeneration. So we have steam coming into the turbine at 9 megapascals and 400 degrees C. It expands to a pressure of 1.6 megapascals, and we bleed some off. We bleed 35% of it off. Yeah, so Y is 0.35. So that's Y is the amount of flow through here that we bleed off. I should actually put that over, indicate that that's over here. And then the rest of the 65% continues on through the turbine. So again, we are, let's see here, put some heat flow in, out, 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 all right? And then we just have heat exchange here in the feedwater heater. So it is let's see, it is an open feedwater heater. So let's see here. We have, we can go through here. Again, very much similar problem. Okay, we have the pump. We can get the work into the pump by knowing the pressure here, and it's a saturated liquid. We can get the enthalpy out of the pump using a conservation of energy on the pump. We know, again, the flow rate, the percentage going through here. At 3, we, again, assuming we have a saturated liquid at 3, we can get the enthalpy because we know the pressure. And then that we're going to assume is also the enthalpy at 4, which is, it's very close to being the same. And then at 9 here also, right? So let's see here. So at 4 and at 9 and at 3. So these are all basically have the same enthalpy because they all have the same pressure and they're all basically saturated liquids. It might be some slightly super cold, but again, it's going to be a very meaningless difference in whether we actually try to worry about that or not. So we can find the work into this pump here because we know the specific volume and we know the pressure difference. So we can find the specific work into the pump, and then we can find the enthalpy coming out of the pump, which is H4 plus this. Now we know pressure and temperature is 6, so we can get enthalpy and entropy. At 7, we know pressure, and now we know the entropy because it's the same as at 6. And so we can figure out that it's in the 2-phase region with a quality factor of about 97%, and we can get the enthalpy. We know the pressure, and now we know the entropy at 8 because it's the same as entropy at 6. So we can get the quality factor about 75%, and we can get the enthalpy, specific enthalpy there too. Now, to get the specific work out of the turbine, what did they actually ask us for? So we have our TS diagram here again. We can see that, and then we have and determine the mass flow rate of steam through the boiler for net power output. Okay, so let's see here. Again, we didn't really get. It's funny because this is a regeneration problem. You'd think that we'd want to know what they'd ask us what this heat was here, and maybe what the utilization factor was, but they didn't. So anyway, we can figure out that the work coming out of the turbine, or the specific work, anyway, we don't know the flow rate, but we know the total power out of the net power out of the system. So we can get the specific work in the turbine is H6 minus H7. Okay, so the enthalpy change here, and then that has this full M6 flowing through it, and then H7, between H7 and H8, that only has 35% or 65%, so 1 minus Y of the mass flow through there. So we know all these values now. We can get the specific work is about 870 kilojoules per kilogram, and then we can get the specific work into the pumps. Because again, we know that all of the mass is flowing all of the mass in the system is flowing through this pump, but only 35% of it is flowing through this pump. No, only 65% of it is flowing through this pump. So 1 minus y. So we have, basically we prorate this, and we can figure out the specific work into these pumps total is prorated by the mass flow rate of 6. So this is the specific work, relative to the mass flow rate at 6. And same with this. And so that's 9.62 kilojoules per kilogram. And so then we can figure out the net specific work out is this minus this. So that's about 860 kilojoules per kilogram. So this is again specific work out relative to the mass flow at 6. And so then we know that then we can get the mass flow rate. This times the mass flow rate is the net power output, and we know both of those things. So again, this is W dot net over M6, and so we can solve for M6, and we get about 29.1 kilograms per second of total flow through here. And again, we have 35% of it coming off here, and then coming through here. So again, a lot of this stuff we didn't really need to, we didn't have to worry about that much. Well, I guess, yeah, we didn't really have to worry about how much was, we have a split here, right? So, but we didn't really worry about how much we were actually taking off of this amount to reheat or regenerate some of this feed water in this open feed water heater, and then how much of it we were running through here to get process heat out. So again, if we wanted those things, we'd have to have some other fraction of how much is going here and how much is going here. But we weren't asked for any of that stuff, so we didn't need to worry about it.